Well, hello everybody, Dave here, and today we're going to continue our lessons on estimating with confidence, this time specifically focusing on dealing with estimating a population proportion. One of the key things about the rest of your education in statistics is to understand that we're really going to focus on what type of data you have, and there's really only two types of data you can have, either categorical or quantitative. And so I would encourage you to separate your notebook into these topics because for chapter 8, 9, and 10, we're going to deal with this exact lesson format where we're going to deal with proportions, then we're going to deal with means. It's important again that you have a good understanding of chapter 7 because we're really going to exploit the use of sampling distributions in this lesson. So let's imagine that we have a barrel full of beads with thousands and thousands and thousands of beads, and we want to create a confidence interval that we believe can capture to within whatever confidence we're looking for the true proportion of red beads within that barrel. And so we take a SRS of 251 beads, we count them, and we find out that 107 of those beads are red beads. Well, that gives us a sample proportion. You know it's a sample proportion because it's got a hat on top of 107 over 251, or 0.426. Now, it's important to remember that we aren't trying to actually estimate the value of P. We're trying to find a confidence interval that we have confidence that it has captured the true value of P. And so in order to do this, we have to create a confidence interval. And the first thing we have to do is recognize that conditions are going to mean everything. And so one of these things with statistics is a formatting for whether it be confidence intervals or significance testing, this idea of how much information do we have to justify the calculations we're going to do. So in order to use a sampling distribution to create our confidence interval, we're going to have to satisfy conditions. The first condition's already been satisfied because the sample has been taken using a random sampling, an SRS in this case. Now we have to check the other conditions to satisfy whether our sampling distribution is going to be normal to begin with. So you'll recall that there's two other conditions that we have to deal with. The first is the 10% condition, which again is recognizing the fact that we are sampling without replacement, but at the same time, we're trying to assume independence so that we can calculate the standard deviation of our sampling distribution using a binomial approach. The large counts condition, which we're showing here on this screen as NP and N times 1 minus P, again is dealing with successes and failures. And in order to assume that a distribution is going to be normal, we're going to have to make sure that these large counts are at least 10. And again, this comes back from chapter 6, where we learned that the larger the sample size, the more a binomial distribution becomes a normal distribution. So this large counts is really a normal condition that we're going to use to satisfy using a normal condition type scenario. In addition, once we've satisfied that, we know that a sampling distribution by definition should center on the true proportion P. And so a sampling distribution of all the P hats is going to give us this value of P. And the standard deviation, of course, because we've satisfied the 10% condition, will be P times 1 minus P over N, the square root of that. The problem in this case, and this is something that you're going to see a lot in statistics, is we no longer have the information for the population parameter P, which means that we can't just simply calculate the standard deviation. So what do? Well, the answer is we're dealing with statistics. And in statistics, it doesn't have to be perfect. It just has to be close enough. And so in our case, we're going to make an assumption that if we don't have P, in large samples, P hat will be close enough to P, and so we're just going to use P hat to check the normal condition and therefore calculate the standard deviation down the road. So these conditions that I've talked about here, you're going to want to put a big star on your notes beside this, because whenever we're dealing with any sort of statistical calculation now that involves models, you're going to have to satisfy conditions to justify the use of a normal distribution or whatever type of distribution we have. So the random condition, it's obviously the most important because without random selection, you're doomed. Random assignment in experimentation is important as well. With 10% condition, key note here, it's sampling without replacement. If we were sampling with replacement, well then that would represent an independent case. But when it's not with replacement, then you have to check the 10% condition so that we can at least assume independence so that, again, we can talk about the case of binomial standard deviations and things like that, which we will then apply to our approximated binomial as a normal, given that the large counts condition has been satisfied. So our goal in life when it comes to creating this confidence interval is to satisfy the conditions such that the sampling distribution is going to give us the information we need to create our confidence interval. There's another problem, though, that we have to talk about, and it's in terms of the notations and the terms that we're going to use. Remember from last lesson that we defined the confidence interval as the statistic or the point estimate plus or minus the critical value times the standard deviation of the statistic. Remember that back to quantity there, critical value times standard deviation, that's something that we called the margin of error. Well, in the case yesterday, we dealt with a case where we had information of the population that allowed us to calculate the standard deviation itself. In this case, however, we don't have the value of the population parameter p, which means that we can't actually calculate the standard deviation of the statistic. However, just like we did with the large counts, we're going to estimate it because we've taken a large sample that p hat is somewhere around p. We're going to replace p with p hat so that we can calculate a standard deviation with p hat times 1 minus p hat, all that divided by n and square rooted, but we can't call that the standard deviation of the statistic anymore because we're no longer using the population parameter p. So we need a new term to describe this, and we're going to call this thing the standard error. So standard deviation is when we use the population parameter. Standard error is if we have to estimate the population parameter with the sample proportion, in this case, p hat. So now we have all the information we need to actually create our confidence interval. And again, we have our point estimate or our statistic, and we understand how to calculate the standard deviation because we're actually finding the standard error. But that quantity critical value is something that in the last lesson we talked about as an approximation using the empirical rule, or the 68, 95, 99.7 rule. Because you remember that normal distributions are distributed according to a 1 standard deviation, 2 standard deviations, and 3 standard deviations idea, where it represents 68%, 95%, and 99.7% of the data in between. However, those are approximations, and if we want to find the actual critical value that results in the probability of 95% of the data in between it, then we actually need to do a little bit of geometry with this normal distribution. And you've all used normal CDF at this point, and you understand that normal CDF, you can define the lower bound and the upper bound. Well, what if we don't know what the Z star value is? What if we don't actually know what the critical value is? Well, in that case, we have to use an inverse norm suggestion. And in this case, 0.95 will only work if we're dealing with calculators that have the center function that allow you to just find the probability around the center. But for older calculators, you're going to have to be a little sneakier about it and calculate either the upper critical value or the lower critical value. You'll notice that the critical value on the diagram here is the same, but one has a negative sign. That's because, of course, we know that normal distributions are very nicely symmetric around the center, which in this case is 0. So if we talk about the upper critical value, then the area behind it isn't 0.95. It's 0.95 plus that lower tail, that left tail probability of 0.025. So to find the critical value that results in a 95% probability in between it, you actually have to do an inverse norm of 0.975 so that you find what that upper critical value is. Conversely, you could also find the inverse norm of 0.025, and that will give you the lower critical value. You would just have to interpret that negative sign as being the left of the mean. Either way you go, anytime we have a confidence interval of some unique value, say 80%, then you wouldn't actually calculate an inverse norm of 0.8. You'd have to understand that if it's 80% around the center, then that means there's 20% outside of the center, which means the lower tail would actually represent 10%. So you would have to do an inverse norm of 0.9. And so I would encourage you to play around with calculating exotic critical values, because really that's the only hurdle that you have to jump over when it comes to confidence intervals, because outside of that, the rest of it is pretty straightforward. So from here on in, instead of using 2 as a critical value for a 95% confidence interval, we're going to go ahead and use 1.96. So just as a follow-up example to this calculation of a critical value, here's an example where we're looking for an 80% confidence interval. And in this case, just like I said before, if we have a 0.8 probability centered around the center, then that means there's 0.2 or 20% outside the center. And because it's a symmetric shape, we're going to have a tail probability of the lower and upper tail of 0.1 or 10%, which means that if we want to find what the critical value is, we can either do an inverse norm of 0.9, or you can go to table A and you can find where you get this value of a lower tail of 0.1. And you can see from table A that you can't get it exactly 0.1, but you can get pretty close. And the closest entry gives you a Z star value. Now again, that star is important. That's a notation representing critical value, not just a Z score. And the Z star value in this case would be 1.28. Notice that they have dropped the negative sign in the overall statement of Z star, because with a confidence interval, we're going to have a plus or minus anyways. And so we don't need to interpret that negative sign as anything except for around the center to the left. So we can go ahead and summarize everything that we now know to find the one sample Z interval for a population proportion. And again, we're not trying to find the exact value of P, and we're not trying to estimate P. We're just simply trying to find an interval from which we have a certain confidence level that the true proportion is captured by it. And so the general equation for the confidence interval is given at the top there, but now we can fill in the specific information that we have. Again, we have our sample proportion, which is our test statistic, plus or minus Z star. That star is not a multiplication, but again, Z star is multiplied by the standard error in this case, but Z star is the notation for critical value, times the standard error. Notice it's standard error and not standard deviation because we have estimated P to be P hat for the sake of calculating the standard deviation. And so this equation here gives us what our confidence interval is, so long as our conditions are met. So the random condition, the 10% condition, and the large counts condition all have to be satisfied for us to be able to calculate the confidence interval using this equation here. So let's go ahead and do an example of this. Let's go back to our beads question, and now we can actually use our sample proportion. We've already checked the conditions so we know that we're satisfied. But let's say that we want to find a 90% confidence level, in which case we have to calculate a new Z star value. And again, I've gone through this in a previous slide, so it's good practice to come up with the same number as me. But with a 90% confidence level, you get a Z star of 1.645. And so taking all this information, we can simply plug and chug into our confidence interval equation. And we have our P hat, we have our Z star, and we can calculate the standard error using these values. And once you do, you end up with an interval of a lower bound of 0.375 and an upper bound of 0.477. Now, students ask me all the time, what kind of work do we have to show? And I would very strongly encourage you to show the original equation of your confidence interval, because it's indicating that you understand that we're calculating the standard error and not the standard deviation. It's then showing a substitution of values, which is equally important, because now you're showing, here's my critical value and here are my actual proportions that I'm using. And then when you get to the end, yes, the plus or minus is indeed an interval, but remember that we've talked about a scripting, which means that we talk about it in terms of a lower bound to an upper bound. So it's always important to take this interval with the plus or minus and actually create the lower bound and upper bound to show that you understand that it is in between those values. There may be subsequent questions for a particular free response that asks you to interpret a particular value, so you would have to do this calculation somewhere down the road anyway. Demonstration of understanding is easily one of the most important things in statistics, so do your best to show that. So the script that you can see here is we are 90% confident that the interval from 0.375 to 0.477 captures the true proportion of red beads in the container. Please note that we have discussed it in terms of confidence and not in terms of chance. We have shown the lower bound and upper bound, and we are talking about it in context to the problem, which is the true proportion of red beads. If you didn't understand the problem, you may just say the true proportion of the population. Well, that's not going to be good enough for anybody who's trying to assess you. So this is an important element to this confidence interval calculation, is that we've satisfied conditions, we've now done the calculations, we've now stated the conclusion to the proper scripting, and then if we have a subsequent question like your teacher claims 50% of the beads are red, use your interval to comment on this claim. Now we have the interval. This 0.5 does not fall within the interval, and because of that, we have reason to doubt it. So this is the cool part of a confidence interval, is we can start to interpret the meaning of statements once we have this interval in place. Because if the teacher said that it was 0.4, that would fall within the interval, and now we would have reason to believe that, yeah, that's probably right based upon our confidence interval. So I just talked you through the whole question itself and this process for solution. And the first thing you always have to do with any statistical problem now that we have all of these steps to go through is we have to state what parameters are we trying to estimate, what are we looking for, what confidence level are we trying to talk about. And so make sure that you split this up into state, plan, do, conclude, or at minimum have this information within your solution, because we're all looking for this, because you really do have to go through this process in order to justify all the calculations you do. Most students tend to just focus on the calculation end because they think that stats is all about the math, but truly in order to justify the use of that math, state and plan are absolutely essential. Once you've stated the parameters and the confidence level you're talking about, now the plan is we're going to check the conditions. And so if we're going to use a one-sample Z confidence interval, then we had better satisfy that using random 10% and the large counts condition. Once you've done that, the do part is great because now you get to do the calculations, you build your equation, you substitute in your values, you get your interval, you actually calculate the lower bound and upper bound, and within the conclude, you use the script and you interpret that interval in the context of the problem. And if there's any subsequent questions where there's a claim being made, if that value falls in the interval, then you have reason to believe that that could be true. And if it doesn't fall in the interval, you have reason to doubt that that claim is true. Now, this leads us to one of the trickier parts of statistical studies in general, and that's trying to figure out the sample size that we want to choose. And there's lots of different rules and thoughts as to why you select a certain number of people. Sometimes it could be because we want to exploit the central limit theorem, perhaps. In some cases, it's because just a logistical reason. Too many people, it's just going to be too much. In some cases, it's going to be based upon the 10% condition. We got to make sure that that sample size is less than that. But at the same time, when it comes to a confidence interval, it can directly affect the margin of error that we have for that interval. And so remember that when we were talking about the increase in confidence interval, we were talking about it in terms of, well, just increase the interval size, that will increase the confidence because we are capturing more of the data. So to go from a 95% to a 99%, we're not actually narrowing it. We're not more confident because we're more accurate. We're more confident because we're actually wider in our margin of error. Well, what if we want a specific margin of error? What if we only want it to be 0.05 or 0.1 or something like that? Well, the critical value is something that's going to be locked in based upon the confidence level. P hat is going to be something that's either estimated or given to us from a previous study. So that value of n, that sample size, is going to be the thing that directly affects our margin of error. And so we can calculate the sample size necessary for a margin of error given two different strategies. The first one is that we are given some value of p hat and we're just going to use a guess for p hat based upon this previous study. And if we don't have a previous p hat to play with, we can simply use 0.5 as a guess because the margin of error will be the largest when the value is 0.5. And what do I mean by that? Well, we know that the top of our standard error is p hat times 1 minus p hat. And the largest product that can exist for those values is when p hat is equal to 0.5. Any other value, the margin of error is going to go down. So again, with statistics, we're just simply trying to find our best guess scenarios. And if our p hat guess of 0.5 is wrong, that's okay because we've really just done that to maximize our potential for the margin of error before we calculate the sample size required to do so. So if they give you a p hat, there's nothing wrong with using that p hat because you can claim that it was from a previous experience. Or you can guess with 0.5, and that's going to ensure that your sample size is going to give you a margin of error that you're looking for, and perhaps even a little smaller if that p hat estimation ends up being incorrect. So this is just what I said when it comes to the sample size. We now have a different way to determine the margin of error, whether we want to increase it or decrease it, based upon just simply playing around with the sample size calculation. And so again, if we have p hat, we can probably use it, but if not, go ahead and guess it as 0.5, and that's going to give us kind of the largest possible margin of, or sample size for that margin of error that we're looking for. So let's take a look at a question like this, and we're saying that we're trying to find a particular confidence level, and within that confidence level, we want a certain margin of error, in this case, 3% or 0.03. And the question is, how large does the sample need to be to satisfy this margin of error requirement? And so when we go to calculate, again, you still have to make sure that we have all the information required. So we do have a Z star value because we're talking about a 95% confidence level. We don't have any proportions from the question, which means we can just go ahead and guess it as 0.5. And now we simply need to calculate what does the sample size need to be such that the margin of error is going to be less than 0.03. And so we plug and chug into the margin of error. And again, it's always important to remember when you're doing this calculation as well, that Z star value is part of the margin of error. Don't forget to include that, or else your sample size calculation is going to be way off. And so we have this value here. We've guessed what p hat is because we weren't given one in the question. We are now doing a little bit of algebra to solve for n. And when we do that, we end up with this value of 1067.111. This is where you have to remember that this is not just simply a mathematical value. There is realism behind this, and in this case, we're dealing with people. And so if it's 1067.111, well, we have two ways to go when it comes to rounding. Because again, there's not a 0.111 of a person. So we could either round down like we normally would with values. But if we round down, take a look at what happens to our standard error. That value becomes a little smaller. And when you have a little smaller number in a fraction, that's actually going to increase it. If we round up to 1068, now the denominator of that standard error is actually a little larger, which ensures that we are going to be less than or equal to 0.03 when we calculate our margin of error. So the general rule of thumb is because the n value is in the denominator, when we calculate our sample size, round up if we need to round it for realism, which we almost always do. So please do. So that concludes our lesson on calculating a confidence interval using sample proportions. And there's a couple of key things to recognize here. The first thing is we don't know the true parameter p. And we're not trying to find the true parameter p, we're simply trying to find an interval that captures the true parameter. And in order to do that, we need to have the critical value based upon the confidence level that we're looking for. We need to estimate p as p hat so that we can satisfy the large counts condition, as well as calculate the standard error, because we can't calculate the standard deviation without p. You also need to satisfy the other conditions. It has to be randomly selected, and it has to satisfy the 10% condition, or else we couldn't even use this equation for standard error at all. And once you've done that, you can simply plug and chug, get your interval, make sure you create the full interval, lower bound to upper bound, understand that you need to conclude using scripting, talking about the lower bound, upper bound, talking about the context of the problem, which will allow you to interpret anything you need to after the fact. Also remember that with this particular formula, we now have a way in which we can justify the sample size based upon a margin of error requirement. If we want a certain level for a margin of error, say 1%, say 5%, we now have a direct way in which we can calculate what sample size we would need to satisfy that particular interval. So let's get to the books and start practicing these confidence intervals. Next up, we're going to deal with sample means. Best of luck to you.